Okay, well, let's go ahead and get started. Welcome to this week's EE310 seminar. It's really our pleasure to have Onur Mutlu with us today. He's a professor of computer science at ETH. And last week, if you recall, we looked back in the past, 60 roughly years ago to see one of the first almost modern computers. But today we're going to be looking to the future, some of the challenges in high performance computing and some of the approaches and research directions which seem most exciting. Onur did his master's and PhD at UT Austin. He was a professor at Carnegie Mellon. He actually still is a professor there, even though he's also at ETH. And right now he's a visiting professor at Stanford. So he's actually around campus, I think, for the next quarter. Until September, fantastic. So for the next 7 or 8 months, which is really a privilege. In addition to his academic career, he's had some significant industry roles. He worked at Microsoft, I believe, from 2006 to 2009. He started their computer architecture group. And then he's also had roles at AMD, Intel, VMware, and Google. So he's seen computer architecture at scale in some of these very large hyperscaler and semiconductor companies, but also from the academic and research point of view. So it gives me a great pleasure to welcome Onur to our talk today. So thank you very much.
Thank you very much, Craig, for the generous introduction. Thanks, everyone, for coming.
Actually, for some reason, your microphone doesn't appear to be working. Okay. So can I just swap?
Sure.
Great. We'll just ditch that one. And then if you just click that one on.
Is this better? Is this good?
Yeah, that looks great.
Okay. No problem. That's part of the robustness issues I'm going to talk about. So we need things to be robust. Yeah, and we have a lot of ways to go on that one. Okay, as Craig mentioned, I'll be here until September. So if you want to talk to me, feel free to send me an email. If I don't respond, please send me again. I have robustness issues on my email as well. Okay, so this is a broad title. Clearly, I'm not going to cover everything that's interesting about future computing platforms, but I'm going to give you my perspective. And from my perspective, this is what I'm interested in. So in my research, in my group's research, we want to build fundamentally better computers. We work in computer architecture, hardware, software interface, systems, bioinformatics, and security. So we work on a lot of broad things. And this is going to be a broad talk. There may be multiple things that we're going to discuss, but some of them maybe need to be deferred for a future talk, if Craig deems appropriate. Okay, so these are, very quickly, these are what I believe are key issues in future computing platforms. I'm not going to cover all of them in this talk, but I believe we need to design fundamentally robust, meaning secure, reliable, and safe architectures going into the future. I believe we're going to talk a lot about this, so feel free to ask questions. I don't know if you will get to it, but we need to also make architectures fundamentally energy efficient. This will also bring high performance, and this will be memory-centric architectures. Which what we're not going to talk about is, I believe we need to think about latency. We need to reduce latency to access data in our architectures, make access more predictable. And we need to make our architectures even more intelligent and evolving, better than humans, if you will. And if you want better than humans, you need learning agents, essentially hardware that's capable of evolving itself, adapting itself to different circumstances, potentially using machine learning algorithms. So again, this is an exciting area that I'm not going to talk about. And finally, I think we need to specialize for applications. I'm going to motivate this, but again, we're not going to go into a lot of detail. We need to essentially design architectures for very interesting applications that may actually change our future. Does that sound good? Okay, so my plan is to talk about the first two, but probably we're not going to go to the second one even today, depending on your questions. I can go at high bandwidth and maybe cover everything here, but it may not be very intelligent. Okay, so this is how we build computers today. Essentially, we have a transformation hierarchy. I want to give you my perspective first, and then we're going to go into the details of things. This is what computer architecture is traditionally viewed as, essentially microarchitecture and its interface to the software. But I will take a more expanded approach to architecture in this talk. I believe we really need to think things from all the way from devices to algorithms and co-design everything across the stack. So the reason is we want high efficiency, performance, and robustness. And if you want to increase these, I believe we must take the expanded view. And this will become more clear. We need to co-design across the hierarchy and specialize as much as possible to obtain some design goals. And this is already happening in industry, so I'm not talking about anything really new in that sense, but I'll show you some examples of what's happening in industry as well. So before I continue, all of the research that I'm going to talk about are done by these folks, well, or a subset of those folks. And you can learn more about those in our newsletters. And you can find a lot more information about us online. I care a lot about teaching, and I think teaching and research drive each other. Essentially, they're two sides of the same coin. Research is really educating others about something that they didn't know or no one knew before. And teaching is educating others about something that's known to anyone who wanted to care about knowing about it. Okay, we do a lot of open sourcing, so anything that that I'm going to talk about, you can find open source tools online. And all of the papers are online, you can find more about it. Okay, let's jump into the topic. So we're talking about computing platforms. I think if you want to think about computing platforms, we should also think about why do we do computing? No, I should have asked this question, but essentially, I believe we do computing to solve problems. So rewording this answer to gain insight to potentially solve problems. And this is actually Richard Hamming's answer. If you know about Richard Hamming, I'd recommend reading his book, etc. So if you extend this answer, I think we want to enable a better life and future going into the future. So how does a computer solve problems? Anybody who wants to take a guess? Kind of a trick question. Well, today's computers actually solve problems by orchestrating electrons. You might actually imagine computers doing some other stuff, but today we orchestrate electrons. Of course, unfortunately, we cannot easily talk to electrons. That's why we built this transformation hierarchy that I showed you earlier. We have a problem, and we want to communicate that so that it can be solved by electrons, and there's no language that we speak in common. So we build this hierarchy that I'm not going to go into. We express the problem as an algorithm, and then write in a programming language, and then execute it on some system software and on a computer that has an interface, which is implemented using microarchitecture, which is in turn implemented using logic gates, which is in turn implemented using circuits and devices, which operate based on electron physics principles, essentially. Okay, again, I took some time to talk about it, but that's how it is, right? So this interface has been very useful so that we can actually build better computers. Unfortunately, it's limiting us in many ways today. So maybe we need to really think across these interfaces. Okay, so I'm going to take this expanded view, as I mentioned earlier. So before I go further, maybe some of you don't necessarily know about computer architecture. I understand this is a broad class. Computer architecture is really the science and art of designing computing platforms. And in my expanded view, this actually encompasses a lot of things, as I showed you over here. The goal is to achieve a set of design goals from a computing platform. It could be the highest performance on Earth on workloads XYZ, machine learning these days. I'm going to talk a little bit about genomics, for example. It could be the longest battery life in a form factor that fits in your pocket with some cost constraint. It could be the best average performance across all known workloads. This is a more general purpose computing paradigm today. So there could be many, many goals clearly over here. And in the end, you design different types of computers, which I'm going to show you in the next several slides. I believe in the end, many fundamental principles are similar. And in the end, a lot of the systems that we design today are bottlenecked by similar problems that I showed you earlier, but we're going to go into some of these in more detail. Okay, so just to get you thinking, these are some of the platforms that are interesting to us, and there are a variety of platforms. This is my favorite platform, Mr. Bean's self-driving car. We're going to get back to that. And this is a self-driving car a while ago, if you will. If it's required a supercomputer to power this, maybe it's not a great self-driving car, right? And then there could be genome analysis platforms. This is something that's in your pocket, probably. We're going to talk about that also. This is a data center. This is a supercomputer. This is yet another supercomputer. This is a machine learning accelerator, a piece of it, of course. This is a newer version of it. I'm showing you these because I want to show the variety of platforms that we have today. This is an accelerator to essentially do machine learning so that it can guide your car. And this is a system that the same company built to actually do training as well as inference of the data that's collected from the cars. I'm going to go through this relatively quickly. And this is what I mean by people are actually thinking along the direction that I mentioned earlier. People are building across the stack, basically. They're not just building a chip. They're not just building software. They're really building the entire system to really get higher efficiency and high performance across these interesting applications. In this particular case, self-driving cars using machine learning, for example. You can argue that that's good or bad. but that's what's happening right now. And this is a GPU, one of the state-of-the-art ones. This is a wafer scale computer. How many people have seen this? Okay, that's good. This is essentially this big, well, however big a wafer is. This is a new version. Essentially, these folks put a lot of compute elements as well as a lot of memory elements so that they can accelerate machine learning again. And that's the comparison point to the largest GPU at the time. Okay, there are many other chips that people are designing, not just machine learning chips, but also general purpose chips. And many companies are actually doing both machine learning as well as general purpose chips. I'm not going to talk about these in detail. And this was a kind of, from one person's perspective, state of the art in 2019. And in 2021, that grew. I didn't bother to check the 2024 yet, but you can check in that website. And people are also experimenting with other interesting things that are less conventional, if you will. So this is a company in France. It's a startup. They basically have DRAM chips. These are main memory chips, and they put processing inside those main memory chips. So today, you're in an interesting time where people are experimenting with something very different. This is more data-centric or memory-centric. So you can do processing right next to where the data is. I'm going to talk about that a little bit if we get to it, or maybe in a different lecture. And these systems are real today. You can experiment with them. We've been writing papers about it. I'd be happy to talk about them, but I'm not going to get to that right now, at least. And you can also buy FPGAs with configurable architectures where you can couple the FPGA to high bandwidth memory and accelerate applications in a customized way that way. And this is also real. You can do this. There are also other real things that are not necessarily available to us. Samsung, for example, is producing DRAM chips that can do processing inside the chip as well. People are producing memory modules that look like this, where lots of memory is surrounded by a buffer chip that can actually do processing, which is an FPGA over there. Other people are also producing DRAM chips that can do processing inside, mainly to accelerate machine learning. A lot of these are actually driven by machine learning, which is very data intensive. You can see that system companies like Alibaba are also producing their DRAM chips to accelerate recommendation systems or machine learning. And more recently, again, major companies have introduced an interface change that can enable expansion of memory using the Compute Express Link interface. And this has enabled other opportunities like accelerating computation near memory as well. And these companies tend to compete with each other, as you can see. Okay, so the landscape of memory-centric computing is actually growing. And if we get to it, we'll talk about it today, but probably we'll not get to it. And I think I'll also mention that genome sequencing and analysis is also important. And this is something that we're working on. I'll probably briefly mention this today. Okay, I already mentioned this. Essentially, all of these systems, in my opinion, point to this expanded view of computer architecture that's happening in industry today, because we want to get the highest efficiency, performance, and robustness. Any questions? Okay, I'll keep going. So I think as an architect or a system designer, it's also good to ask what kind of a future do we want? And this is where I will actually introduce some of the challenges we have. How many people know what this bridge is? I think some people who attended my talks know. This bridge doesn't exist. It's the Tacoma Narrows Bridge, because this is what happened to it. It basically had a bit flip or a robustness issue. There's another view of it as it happened. You can find videos of it also online. These people are constructing New York, and they're very happy. But if a bit flip happens on the rod over here, they're not going to be happy. So basically, I think robustness problems are going to affect us a lot more going into the future. And I think we need to take a much more rigorous and broad view of handling robustness issues. I think it's all about preventing unforeseen consequences. This is very general, as you can see, right? How can you prevent an unforeseen consequence? Can you build a system that can operate in space, for example, when you cannot predict the consequences? I don't think our systems are up to that task yet. So this system Mr. Bean is relying on is going to be real soon. And do you trust this system is a key question, I think. And how robust are these platforms that we're building or planning to build going into the future? I think we have a serious issue here. So this is a big challenge and opportunity for future. Robustness is a general problem, which encompasses reliability, security, and safety. And we're going to talk about a particular problem, specific problem related to robustness, related to hardware. So the other issue, I think, is, do we want a future that looks like this, where we can breathe, or a future where we cannot breathe? I will argue that sustainability and energy efficiency are key issues. I'm not going to talk a lot more about that. And then we have a lot of problems. Basically, we have problems to solve: climate, congestion, intelligence, understanding, public health, genome analysis. And there are many, many other issues, of course. I will spend a little bit more time on genome analysis because it's an area that we do a lot of work in. And I think this is fascinating. It's a small area of medicine, if you will. There are many applications of this. And today we have sequencing technologies that can generate a lot of data. Unfortunately, we don't have systems that can process the data very efficiently. We've been writing papers about it. I'd be happy to talk about that in some other potential lecture, but I don't have time to talk about this. If you're interested in this, though, we have written a lot of beginner readings. This is an area that's very tough to get into, in my opinion, because it has a lot of terminology that you need to digest. And we've digested that over decades, if you will. I still don't know a lot of the terms. But if you're interested, you can take a look at papers. And I think the future of this is very interesting because we have these devices that are very capable of doing sequencing, but then analysis of the data is really bottlenecked by how fast and efficiently we can process the data. Okay, we have a genomics course that you can take a look, and we've been organizing workshops too. Okay, that's genomics. Genomics is very similar to neural networks, in my opinion. So this is neural networks. This is a talk by Cerebras, that wafer scale company CEO or CTO, I don't remember. But basically, this shows that the models, computation requirements, and memory requirements are both growing exponentially. And whatever is happening in neural networks affects genomics immediately because machine learning is employed in many, many parts of different pipeline, parts of the genomics pipeline. So this is the problem we're facing right now. Essentially, we want high performance in many different applications because we want to solve the toughest and all problems. We're greedy as humans, right? Okay, I will also mention one thing that I'm not going to talk about much, but we're personalizing things, including our devices, more and more into the future. In medicine, for example, we want personalized medicine. We want to do comparative genomics in medicine in a personalized and private way. And these technologies can enable us actually to sequence our genomes and understand what we can use as drugs, for example, on our own potential. This is not happening right now, but I believe this is kind of the goal that we have into the future. And this also happens in other domains. In robotics, for example, you really want to customize these things to the person as opposed to having some general purpose robot doing things. Okay, so I think this is another challenge and opportunity for a future that I'm not going to talk a whole lot about. How do you do personalization and keep it private at the same time in every aspect of life over here? Okay, so what is this lecture about? Essentially, I've been talking to you about very general things. I think we need to, one way of looking at the systems we built today is everything is good. It's perfect, and we keep doing business as usual, and they're going to be good into the future, right? But I'm not going to do that. I think we, as scientists and engineers, we should really question what limits us in designing the best computing architectures for the future. Because the other way of looking at these things is they have a lot of deficiencies. Like if we use them under conditions that they're not really designed for, they're going to break immediately in some cases. And maybe they're good in terms of one metric, but are they really good in terms of some other metric? At what cost do these systems come? We're building these huge hyperscale systems that are really doing, for example, machine learning acceleration. But is this the right way of designing the machine learning acceleration systems, even in that small domain, if you will? So hopefully I will provide some directions for fundamentally better designs, probably in one area. And I will advocate some principled approaches. I think we really need to think about principles in design as opposed to keeping on doing business as usual. Okay, I will also mention that going forward, we have no limit in applications, increasingly demanding applications. People are great dreamers. And as people dream, more applications will come. And as applications push the boundaries, computing platforms become increasingly constrained. The issue is as architectures become better, they actually enable creation of new applications also. So I believe this has happened with machine learning, for example, today, especially with the emergence of GPUs and machine learning accelerators. And going into the future, if we can design much better platforms, maybe we can enable other applications that we cannot think about today. But if you do business as usual, maybe that's not going to happen. Okay, so let me give you my key realization. I think the key realization we have had for a while today is that modern systems are really bottlenecked by data storage and movement in the end. So if you look at a modern system, you have, I should use this probably. You have some compute elements, and then you have some main memory and storage. We're going to try to deconstruct this later when we talk about memory-centric computing. I'm going to focus a lot on main memory, but a lot of the issues are similar in storage as well. And going forward, I believe these systems need to merge so that you can do computing that's immersed with data. Main memory is a critical component of all computing systems today. Whatever you imagine, it has some sort of main memory. And this system must scale in many dimensions: capacity, technology, efficiency, cost, and algorithms we use to manage it to maintain the performance growth and scaling benefits and enable new applications going into the future. So I have processors and caches over here, but replace that with FPGAs, replace that with GPUs, replace that with accelerators. They all have main memory, and they're all bottlenecked by main memory. So I think I already said this. Computing is bottlenecked by data today. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And data is really increasing. We can generate more data than we can process. And this is clear in machine learning, genomics, video. There are many other applications. And we also want to and need to perform more sophisticated analyses on data. And if you look at these, let's say, relatively traditional applications, as they scale, memory immediately becomes a bottleneck. I'm going to give you some numbers soon. And even on the edge end or mobile end, these applications, as they scale, the memory becomes a bottleneck. I'll pick on genome analysis over here. These sequencing machines are extremely capable. They generate a lot of data. And in the end, you want to have scientific discovery or medical advancements. Unfortunately, the processing that you need to do is really bottlenecked by memory in the end. And this is the machine that I mentioned earlier. OK, let me give you some data. We studied some of these workloads, including the TensorFlow system or VP9 video and encoder and decoder. And we found out that on average use cases, more than 60% of the total system energy in a mobile device is spent on data movement, essentially moving data between the memory and the processor so that the processor can operate on it. That's a lot of waste, I will argue. And if you look at large machine learning models, at the time, state-of-the-art edge machine learning accelerator spends more than 90% of its total system energy just on memory access, as well as data movement. So we should probably question these numbers. OK, so memory is critical for energy. Memory is also critical for reliability, which I'm going to focus on first. This is some work that we did with Facebook. We analyzed all of the memory areas that they have in all of their data centers. And essentially, we found out that the server failure rate correlates strongly with the density of the memory that's employed in these systems. So this is the density of the DRAM chip. As the chip becomes denser, you get more server failures. Why? Because you have cells that are less reliable, that's smaller, as well as cells that are more noisy, that are closer to each other. And we're going to talk about that problem. So clearly, this has system-level effects. If you're interested, again, there are papers on all of these topics, and you can learn more. So let me reword the realization that I kind of been talking about. So essentially, modern systems are bottlenecked by memory today. And we've been writing papers about this, an early overview paper that kind of foreshadows what I'm going to talk about in a little bit. So this is what I promised, right? We're going to talk about these key issues. And realistically, we're going to talk about the first one. But feel free to ask questions. So I'm going to go into a little bit more detail right now. Yes, please. Sure.
Like glad that you're talking about robustness, but your buddies from your community have. Are we getting recorded?
Yeah.
Oh, then I don't want to.
OK. No, go ahead. You can delete this
people
part,
online.
maybe.
OK, I'll say it. I'm really glad that you're talking about robust architectures, but your buddies from your community.
I cannot speak for them.
Well, like that means that you guys have to carry that message. For example, even now, right? So as you know very well, that Google and Facebook have publicly talked about not memory, but even compute having major issues with reliability, silent errors and things like that.
That's an example of this one. I agree.
Right, but people from your community have consistently resisted, saying that there is no problem.
Yeah.
So what do you say
I
about
disagree
that?
with them. Basically, I disagree with that. I'm not representing my community, and my community doesn't represent me. This is what I believe in, basically. All of these are important. And we get sometimes the same thing also, right? We submit a paper on solving RowHammer, and somebody says, oh, RowHammer is solved. And we've heard this for 10 years.
There's an online question too,
Okay,
if I can
please.
jump in.
Yes.
So why is there so much of a push into computational resources, bigger, faster computers, but not as much emphasis on algorithms to make things require less resources, especially in the academic and research community? So how can universities, sort of focus more on algorithms as well, which is sort of the other half of the stack?
No, I agree. I think we should be focusing on a lot of things. I think the issue is there's a hype in industry. I'll say it, right? There's a big hype of making money in industry. And I think that kind of clouds our judgment. It's not that I think people are actually working on algorithms, but if you look at the industry, the easiest way to compete and make money is really build bigger systems to accelerate bigger networks. Someone will hopefully come up with a breakthrough with an algorithm, in my opinion, that will fix this issue, but it requires time. And I don't think it's going to come from industry.
I don't want to take up your time, but I think also what's going on is that the way we teach, for example, the folks that do algorithms, they have a very abstract view of the machine.
Yeah.
And many of those people would not take a digital design class, for example, right? The people that do theory, for example. So how do you explain to somebody, how would somebody know, for example, we actually face this, on of our chips, right? That, in certain memory technologies, writes are more expensive than reads. So how could somebody, for example, create an algorithm that has more reads than writes, for example, for whatever reason? But even for people to understand that constraint, it has to percolate through so many layers of abstraction. So I think there is an educational side of it as well, that might need to be revisited.
Yeah, I absolutely agree. I think on the academia side, there's definitely an educational side, because what we talk about is not fundamentally energy efficient systems, for example. I will talk about that. We will see that algorithm architecture, co-design aspect when we talk about data-centric architectures also. So we need to revisit education. It's very hard to revisit industry, in my opinion.
Great, thanks.
Okay. Okay. So as I promised, I think we're going to talk about robust architectures. I'm not even sure if we're going to cover everything over there, but I will hopefully try to cover the energy efficiency a little bit also, but maybe in the future lecture. I'm going to start with this because I have a background in psychology as well, and I like Maslow. Who knows about Maslow? Okay, he's a famous American psychologist who actually developed a theory. Probably this thing is more famous than him or his name. Essentially, this is the hierarchy of needs. It's used in many, many fields. Essentially, this says that you got to be safe and secure before you can think about anything else in the world. And that's why we need to start with robustness, in my opinion. I'm going to deconstruct this when we get to energy efficiency. So keep that in mind. One could argue that energy is more important than anything else, right? Okay, so that's why we're talking about this bridge that got destroyed like this. That's why we're talking about these people. Basically, the problem is when we build systems, computing systems today, we do not seem to have design principles for guaranteeing robustness, reliability, security, and safety. And I think we should shoot for that, essentially. This is very similar to... Okay. Maybe that we have not, like, across the stack, I think we have not figured out how to communicate things across the stack very well. Right? At parts of the stack, I agree, perhaps. There are some principles. But across the stack, once you go from, for example, how to communicate from algorithms to the underlying devices, I don't think we have those principles yet. Even system and memory, for example. Okay. Yeah. Today, for example, we design memory different from controllers, and they don't talk to each other really, right? So that's what I mean. Okay. So we've already discussed that as memory scaled, it becomes unreliable. Denser DRAM chips are more prone to errors. I'm going to focus on a particular problem, as I mentioned. So we're going to talk about DRAM, which is essentially all main memory in today's computers are DRAM, dynamic random access memory. It looks like this virtually. You have a capacitor, which stores data, and you have an access transistor, which enables you to access data together with the bit line and sense amplifiers. And for this memory to work, both the capacitor as well as the access transistor and the sensing structures, they should work perfect. And unfortunately, as you reduce the size of this thing, it becomes more vulnerable to different noise effects. It could be data retention effects, which I'm not going to talk about. It could be noise effects like RowHammer that I'm going to talk about. And there are other effects also that I believe we need to think about and potentially discover. So we've done a lot of work to actually design memory controllers to test these structures. And if you're interested, you can actually buy an FPGA, download our code, and test your own DRAM, maybe figure out some new errors. We open source these. This is the more newer version called DRAM Vendor. And we have a bunch of prototypes, and we help people who try to bring this up. And together with Intel, in 2012 or so, we actually found out that you can predictably induce errors in most DRAM memory chips. And this is the idea of RowHammer, essentially. It's a simple hardware failure mechanism that causes bit flips, which causes, in turn, a system security vulnerability. It's a robustness problem. So it could be actually a system safety vulnerability. It could be an availability problem. It could be many things. But I'm going to talk about the security aspect a little bit because security community tends to be quite excited about these bit flips, as you will see. And people are writing articles that look like this. Forget software, now hackers are exploiting physics. I like this because this kind of bridges the focus on the software and puts the focus on hardware in relatively mainstream media. So what's the problem? Essentially, remember those little cells that I showed you? Each DRAM consists of rows, or any memory consists of rows, and each row is thousands of those cells. And if you want to activate or access one cell or one word, let's say, you need to activate a row, which means that you apply high voltage to the word line. This is called opening the row or activating DRAM. If you want to access some other word or some other row, you need to deactivate this row. It's called pre-charge in DRAM, apply low voltage. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, it turns out in modern DRAM chips, some vulnerable cells in physically adjacent rows get flipped. So they lose their data. There are a lot of mechanics underneath it. There's a lot of analysis, which I'm not going to go into in this particular talk, which is a broad talk. But essentially, this happens in real chips. And that's the matter of fact. And it should not happen in real chips because you should really not be able to change any data that doesn't belong to this row. And you should not be able to change any data that belongs to this row also because you're not writing anything to this row by activating it. So this is a data corruption, essentially, or a bit flip. And at the time, we tested a bunch of chips from 3 major manufacturers. There are only 3 major DRAM manufacturers in the world. And we found out that more than 80% of the chips are vulnerable. Now, fast forward 5 years later, all of the chips that we tested in the field are vulnerable. So this is a scaling problem. Why it's a scaling problem? So this is the data that we published in 2014. Basically, all of the chips that were manufactured between 2012 and 2013 were vulnerable. No chip that we tested before 2010, manufactured before 2000, was vulnerable. Basically, cells become closer to each other and smaller as technology node size reduces. As a result, the noise that the cells have increases. That's the high-level explanation of it. There are a lot of low-level issues, of course, that we're not going to go into. So this problem is expected to get worse as cells become smaller. And we want cells to be smaller so that we can get higher capacity memories. So either you can give up capacity and fix this problem, potentially, but that is not going to enable bigger applications for you. OK, so what's the issue? If you have a bit flip like this, now you can write software that can exploit this. So this is a program that we released at that time. It's essentially a user-level program with these 6 lines. It ping-pongs activates to rows X and Y. And if the chip is vulnerable, hopefully you'll get bit flips. Now you can sandwich one row between X and Y so that you can get even more bit flips. It's called double-sided RowHammer, and it's been exploited in attacks recently. I'm not going to talk about this program, but this program is written this way so that it can bypass the CPU caches as well as the row buffers in DRAM. Please stop me if you have questions. OK, so we basically showed that you can get bit flips in real systems. There's nothing special about Intel and AMD. All systems are essentially vulnerable. And this is a real reliability and security issue. And we mentioned in our paper that one can take over an otherwise secure system. So I'm going to read the first sentence. Memory isolation is a key property of a reliable and secure computing system. And access to one memory address should not have unintended side effects on data stored in other addresses. And we said that based on what we demonstrated, someone can build a program that can hijack your computer, crash your computer, essentially do almost whatever they want with that computer without having any privileged access to that computer. And these good folks from Google Project Zero read our paper, and they demonstrate essentially what we kind of suggested. This is a copy and paste from their blog post, and I recommend reading their, watching their YouTube presentation on Black Hat if you're interested. They basically said they built 2 working privilege escalation exploits that use the RowHammer effect that they replicated on their own systems. And I'm not going to talk about both of them, but one of them is very interesting. Essentially, a user-level process that they built was able to induce these bit flips to gain kernel privileges when it's run on x86-64 Linux. And the key idea is that when you run this process, it is able to induce bit flips in its own page table entries. And if you're able to induce a bit flip in your own page table entry that points to your own page table, you basically can flip the right bits such that you can gain write access to your own page table. So this circumvents modern virtual memory protection mechanisms because these bit flips happen at a physical level. OK, so later, there are in some works that try to protect the page tables, for example, to solve the security aspects of it. I don't think they're complete solutions, but there's actually a lot of operating system work that's going on this topic also right now. I believe we need to solve the problem more fundamentally. OK, so this became famous as the DRAM RowHammer vulnerability. And some famous hacker on the internet said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're at. So if you're stuck in this room, don't worry. Keep banging on the wall, and hopefully that wall will that door will magically open if RowHammer is in place. Okay.
Question though, is this a failure of the design tools or the validation or simulation tools? I mean, if you look back at what sort of triggered this, or is it hard to root cause?
That's a good question. So of course, I don't know for sure, but people can potentially predict some of these things by doing like vulnerability analysis early on. People can have better testing methodologies. So it could be a failure of testing, certainly, but it could also be a failure of looking for the right thing before it happens, right? I believe it's a combination of both.
And has it improved in the last few years?
I'm going to talk about that. Okay. You can ask that question if you haven't got the answer recently. Okay. Okay. So why is this interesting? So security folks have always been interested in bit flips. So people have demonstrated, for example, if you have a bit flip, your cryptographic protocols are essentially useless, if you will. But these are real bit flips that software can induce now. So this became a very interesting playground for security folks to show innovative attacks. So these folks from TU Grads, for example, showed that using RowHammer bit flips, they could take over a remote computer through JavaScript, which is fascinating. These folks from TU Amsterdam showed that someone can download this app, and this app essentially figures out the locations that it can flip on your phone. It can take over your phone, essentially. These are very interesting security papers, and if you're interested, you can take a look at them. These folks show that you could actually do these attacks much faster using a GPU, because it could hammer memory much faster with a lot of accesses. These folks show that you could actually do this in a remote machine through the remote direct memory access engine infrastructure, and these folks showed essentially the same thing. More recently, these folks show that even though you may not be able to take over a machine, you can break confidentiality, meaning you can read data from a location that you don't have access to. And also more recently, people have shown that machine learning inference mechanisms are vulnerable to essentially, let's say, safety problems. And otherwise, reasonably accurate machine learning inference can drop significantly in accuracy if someone actually causes these bit flips on your machine. So machine learning accelerator is also potentially vulnerable. And people have been developing attacks, both industry and academia. Interestingly, Google introduced this half-double attack that I'm not going to talk about, but if you're interested, you can take a look at this on your own. So people actually have nice pictures online also that I found. This could be a solution to your problems, potentially getting rid of your computers. In fact, people have suggested that. Why don't we use DDR3 RowHammer, or not vulnerable DDR3? I think that's a step in the wrong direction, right? We want to actually build more powerful, more capable computers to solve problems. We really want to scale, but we want to scale in a robust manner. Okay, so how do you solve the problem? So that's clear, this is not going to be our solution. The solution that industry adopted is changing the refresh rate in the memory controller, because this is what could be done. This is the only thing that could be done on chips that are vulnerable in the field. Basically, you can change in the BIOS the refresh rate. You can increase the refresh rate. If you increase the refresh rate, the number of activations you need to induce a bit flip will not be possible within the refresh interval. So Apple, for example, did not tell how much they increased the refresh rate, but probably by 2x or so. In our paper, I'm not going to go through this in detail, but in our paper, we show that if you want to get rid of every single bit flip that we demonstrated at the time, you need to increase the refresh rate by 7x. Clearly, we don't want to increase the refresh rate, because refresh is essentially you keep accessing memory once in a while so that you keep data intact. If you increase the refresh rate, you're wasting energy, and you're also wasting performance, because our refreshes actually interfere with accesses that are coming from the processors. So this was the only solution. Now we're going to talk about what's been happening since then a little bit. Okay. So essentially, this was adopted widely by industry. So I believe we need to take a more principled approach. So we need to design fundamentally secure computing architectures. We need to somehow predict and prevent such safety issues. Again, I keep using safety, but it's really a robustness issue. And maybe Subhashish will argue that, oh, we know all these principles, but I will argue that we don't yet know everything. Or at least we may know the principles, but the principles may come at a high cost. So maybe we need to lower the cost of enabling this robustness. Okay, so our solution, I'm going to talk about this very briefly. I believe this is a slightly more intelligent solution than increasing the refresh rate. The idea is very probabilistic. Essentially, after closing a row, the memory controller or the DRAM chip activates or refreshes one or both of its rows, or both of the adjacent rows with very low probability. So the probability can be set to some value that will hopefully give you a good reliability guarantee. And of course, this probability is dependent on how many activations will cause a bit flip. If that number is like 100,000 or so, which was the case at the time we tested these chips in 2012, this probability may be okay. If that number is 100, meaning if you activate a row 100 times and then that causes a bit flip, you need to increase that probability, which means that this will increase the refreshes that you do if that number goes down. And that number keeps going down. I'm going to go show you that number in a little bit. So basically, if you're paranoid, you can adjust the value of P also. So the advantage of this solution is it doesn't have any storage cost. You don't need to track, for example, which rows are activated how many times and try to do something about it. You don't track anything because it's probabilistic. And hopefully, it gives you a good performance overhead depending on that number, RowHammer threshold. And it's also stateless. OK, so it can be implemented in the DRAM chip. It could be implemented in the memory controller. I'm not going to talk about that in detail. And this was actually implemented. A variant of this was implemented in Intel memory controllers. They called it PTRR. And in the BIOS of the chips that are capable of this, you can actually choose your RowHammer solution. It could be hardware RowHammer protection or 2x refresh. If you choose hardware RowHammer protection, you need to set your own probability. Hopefully, you won't set every other activation. And that's going to be not so good. Right? OK. So I think this is a step in the right direction because it's a slightly more intelligent controller that can help with scaling issues, security issues, robustness issues. Right? I think this controller needs to become more intelligent going into the future. I don't think this is enough. And actually, our results show that this is not enough yet. OK, so this is the first RowHammer analysis paper. We have written more papers on it. And this is the latest one, although it doesn't cover the most recent research that I'm going to talk about. Any questions? Yes, please.
But with P is equal to 1.
Yes, well, no.
Sorry, can you repeat the question?
OK, the question is, that's a very good question, actually. Is the solution proposed by Apple, which is increasing the refresh rate across the board, the same as our solution, but P is equal to 1? No. So P is equal to 1 means that every time the memory controller closes the row, it refreshes the adjacent row, only the adjacent row. But increasing the refresh rate across the board means that you basically refresh all rows more frequently. So actually, the solution that's used by industry is worse. And we've shown that actually in many papers. So you really need to do a targeted or selective refresh. Whereas the increasing the refresh rate across the board is not selective. It's really all rows.
If P is equal to 1, with that within the approach would still be better than
So, OK, that depends on the threshold, RowHammer threshold, essentially. If the RowHammer threshold is very low, P is equal to 1 actually is not that great. So, OK, maybe that depends. Sorry, that depends on the access pattern of the application, right? If the access pattern of the application is such that you're opening and closing many rows, P is equal to 1 is actually refreshing a lot of adjacent. OK, so there's a curve. I don't know. We never set P equal to 1 because that's a bad idea in general. But you can actually look at that curve. Yeah, that's a very good question also. But in the end, none of these solutions, increasing the refresh rate or probabilistic adjacent row activation, work well as the RowHammer threshold goes down. And later work showed that. OK, any other questions? Yes, please. So that's an excellent question also. So
can you repeat the question?
Yeah. How much does error correction help? So existing systems employ error correction inside the DRAM chip as well as the memory controller. And they're very simple error correction mechanisms in general, especially inside the DRAM chip. So if you use a simple error correction mechanism, it helps, but it doesn't get rid of all of the bit flips. In our papers, we showed that in some cases, you get 8-bit flips in a ECC code work. And most error correction mechanisms today cannot correct those bit flips. Now, there's a little bit more nuance to this if you have chip kill, etc. But in the end, you're vulnerable with error correction. You may reduce the vulnerability.
Thanks.
OK. So let me tell you about what happened in 2020 and 2024. Again, I'm not going to go into a whole lot of detail. I have another detailed RowHammer lecture that I'm happy to give some other time. So RowHammer is basically getting much worse because it's a technology scaling problem. We tested in 2020 in this particular paper more than 1,500 DRAM chips again. And we showed that newer chips are more vulnerable. You get more bit flips that are happening earlier. For example, They're new chips whose weakest cells fail after only 4,800 hammers. This is double-sided, so it's really 9,600 activations in the end. And that number was 100,000 or so in 2012. So it's basically reducing by around 10x within the course of 5 years or so, or 7 years. Okay, I'm not going to talk about everything over here, but essentially what this paper showed was existing mitigation mechanisms are not effective at future technology nodes. So if you scale this number, 4,800 to 500 or 1,000, we show that existing mitigation mechanisms do not work. Do not work, meaning that they induce a large amount of performance overhead. And we don't want a huge amount of performance overhead. Okay, so we also show that industry adapted solutions do not work. I'm going to talk about that very briefly. And they're very poor, in fact. So what the industry did, after Intel introduced their memory controller, DRAM manufacturers said, oh, we solved the problem. This is what I mentioned earlier, right? We solved the problem, and everybody believed them. This is fascinating, I think. The industry did not say how they solved the problem, did not disclose their solutions. They just said, it's done. And Intel, as a result, pulled off their memory controller solution. So they didn't develop anything further. So we, of course, as academic, you need to question whether that's the case, right? So we took a bunch of DRAM chips, and we basically attacked them. Of course, attacking was not easy, but industry introduced internally in the DRAM chips was variants of what we have described in our paper as solutions. So some of the chips, for example, kept track of some number of rows, and they had counters that counted the activations to each row. And after that activation count reached a threshold, they would refresh adjacent rows. This is what we hypothesized that the chip does. And we figured out that actually chips already do that. Unfortunately, they're not secure. They're not perfectly secure because these counters are of limited size. You can keep track of, for example, 4 rows or 16 rows. So we introduced an attack that would hammer more rows than these counters can keep track of. That's the idea. That's the trespass attack. So it requires a lot of reverse engineering using the FPGA-based infrastructure that I mentioned. And we later reverse engineered essentially everything about what happens inside the DRAM chip to protect against RowHammer. So maybe industry banked on the fact that this could not be done, but this is relatively easily done. Imagine we're doing this on an academic budget. If someone really interested wants to put a lot of money into it, they can easily reverse engineer all of these things. So you're not secure, basically, in the end. Okay, so this is a poor RowHammer solution. This is what I would like to describe. This is the industry solution, and you can bypass it. Right? You don't want to build fences like this. So basically, key takeaway is RowHammer is still an open problem, and security by obscurity is likely not a good solution. Now, you may argue that that was 2020. What happened since then? Okay, before that, I should probably say that clearly industry has been putting in more intelligence inside the DRAM chips, except they're not doing it in a robust way. So I believe these are all steps in the right direction, actually. What was wrong was perhaps not exposing what was inside or not vetting and making sure that it was completely robust. So I think intelligent control is a good idea. So these works that I mentioned that show that existing chips are vulnerable triggered a lot of churn in industry. And JEDEC, which is the committee that provides standards in main memory, they met many, many times. And they basically put out a bunch of white papers, and they're working on it still. And finally, last year, in 2023, SK Hynix published a short paper where they talk about their RowHammer solutions, a bunch of solutions. A lot of them are variants of what we have described in the past. One solution is basically I'll show you the DRAM chips over here. Essentially, with every row in DRAM, you have a counter which keeps track of how many times the row is activated. And internally, if you go over an activation count, you refresh something. We don't know exactly because the paper doesn't describe in detail. And they claim that they reduced the RowHammer vulnerability to 7%. So again, I believe this is actually a step in the right direction, but this is also very high overhead, right? Every row has a counter associated with it. This is something that DRAM manufacturers did not want to do for many, many decades. If you went to them and told them, oh, I want some intelligence in your DRAM chip, can I count something? They would kick you out of the door, probably. And they did it, finally, and after 10 years. So is this secure? Maybe you're going to ask that, I don't know. I don't believe it's secure, but it needs to be seen, yes.
So an online question.
Yes.
What about the device and physics level? Has there been an effort to make the underlying cells behave better, even though the scaling pressures are continuing to make the problem worse?
No, that's an outstanding question. I think, I believe the answer is yes. There are also papers related to this. Usually, a good solution comes with very high cost. And I believe this is where DRAM manufacturers did a good, well, I don't know about the good job, but they actually did the best they can within the cost constraints that they can. Because I don't believe RowHammer is getting as worse as it could get without these device or circuit level solutions. But they don't disclose exactly what they did internally. Yes. Yeah, I'm going to...
I repeat the question, please.
Okay, sorry. What about, yeah, are they vulnerable? Yeah. So, okay, very good question. So basically, what about different memory technologies, RAM or PCM, et cetera? Are they vulnerable to this type of effect? So I believe all technologies are vulnerable to some sort of read disturbance. You see this, for example, in flash memory, et cetera. The question is how much? We don't know. A lot of those technologies, like emerging memory technologies, are not manufactured at the scales and the sizes that we have DRAM or flash memory is today. So we don't know if they're really vulnerable as they scale to that. But people have demonstrated, at least in simulation, there's write disturbance effects that are somewhat similar to RowHammer. And some technologies, there are also read disturbance effects also. Yes.
So requires some of these solutions, they propose like a new architecture or something like that. So I'm just wondering then for the current like generation of chips, right? If they do have these vulnerabilities and there's no way of solving it through software, right? Then doesn't it leave the current chips very vulnerable? Like any device that has that chip vulnerable?
Yes.
Sorry, can you repeat the
question?
So,
okay, basically, the question is, the current chips that don't necessarily have these increased level of protection, aren't they vulnerable? Or any device that uses those chips vulnerable? And the answer is yes, essentially.
And is that an issue going forward?
Yes.
So is that an issue going forward then? It's because we have so many devices, every year it gets produced, right? And it's kind of cumulative, basically. So wouldn't this be an issue, even if this issue was solved tomorrow, because there's so many devices that use these current chips? Yeah. Is that going to be a big issue?
So I don't know. I cannot predict the future. I believe it could be an issue under different circumstances. So if you use these devices in places where we're not designed for, under harsh conditions, for example, it could be an issue. Now, that said, there are still solutions, but in DDR4 chips that are commonly employed in the field, there are solutions in place. So a RowHammer attack is harder to perform. But if you actually are very determined, potentially you could perform it also. So in the end, I think what I'm going to get at is basically we want principled architectures that can be upgraded in the field so that they can fix these errors. So they can do online testing, for example, or online updates, and that can be patched in the field so that if you discover something like this, you could upgrade your memory controller, and hopefully that will fix at least the most important problems. So that's what I'm going to argue for in a little bit.
So then this solution doesn't...
Sorry. So this solution then doesn't work, right? For let's say updating old chips.
That's correct. Yeah, this solution doesn't work. This is a hard-coded solution in a particular DRAM chip. It's not even clear this is going to be adopted in the field, but at least the good news is at least the DRAM vendors are writing papers about it, and they're using the word RowHammer, if you will, 10 years later, right? Okay. There was another question, but I'll go otherwise. Okay. So, okay, of course, Samsung had to write a paper about it too. If you're interested, you can take a look at it. It's very hard to read paper, but they have some solution which I believe is broken. Okay. Okay, so you can ask the question. There are a lot of good questions that you asked. Another question to ask is, are we really now RowHammer free in 2024 and beyond? Or are there any other bit flip mechanisms? And this is something that we published in ISCA last year. I'll give you the basic idea. Essentially, there are other mechanisms that we will find out, in my opinion, and this is one of the mechanisms. And row press is the fact that you can keep a DRAM row open for a long time, and this causes bit flips in adjacent rows. You don't need many activations, essentially. These bit flips do not require many activations. In some cases, for example, you can reduce the activation count by 10x to 100x compared to regular RowHammer. I'm going to show you a demonstration of that. Only one activation is enough in some cases, actually, but this violates a lot of timing parameters. And this bypass mitigations that detect high activation counts. Those counters, for example, that I showed you earlier in the SK Hynix chip, if they don't take this into account, then they're going to be vulnerable to this effect. So we're back to this picture over here. Okay, so this is a demonstration. In RowHammer, you activate an aggressor row as fast as possible at the highest rate possible, every 36 nanoseconds, for example, or that's the distance between two activations. And you can induce bit flips with 47K activations. With row press, you keep the row open a little bit longer, and you need only 5K activations. So if your defense mechanism doesn't take this into account, you basically can get bit flips. Okay, I'll keep that as is. So yes.
You're probably getting close to time.
Oh, okay, close to time. Okay, there are many good questions. Okay, so there are many more results and analyses in the paper that you can take a look. I believe there's more to come, and this is an interesting area to look into. Actually, I delivered a lecture on RowHammer at Stanford that was hosted by Subhashish Mitra, Professor Mitra over here. You can take a look at it online. So what else is going to go on? I'm not going to talk about everything, and since we're out of time almost, as I expected. There's more going on in RowHammer. You can take a look at major conferences. I believe there are interesting things in security and architecture and devices. And we're going to keep going on this in this area. Let me generalize a little bit. I think we're talking about robustness in general, right? And DRAM is not the only technology, as kind of indicated from the back. DRAM is clearly becoming less reliable, more vulnerable. And I believe there may be some other errors that are slipping into the field that will slip into the field. And maybe we need to have a more fresh approach to DRAM robustness going into the future with RowHammer and read disturbance effects as a special part. So these errors can also pose security vulnerabilities. There are other technologies like flash memory that are clearly vulnerable to read disturbance that I'm not going to talk about. And what about emerging technologies? I think emerging technologies are very interesting. Unfortunately, none of them are as close to DRAM or flash memory today. But I think we should think about it. So we've done a lot of work in phase change memory that I'm not going to talk about. This is a fascinating area on STT-MRAM, etc. as well. And in general, these emerging technologies have a lot of issues. Endurance is one problem. So immediately you need an intelligent controller to fix the issues. And there are other robustness issues that I'm not going to talk about over here. So how do we architect robust memory systems? I think again, I don't know I have the answers. I don't believe that I have the answers, but I think I have a methodology to get to the answers. So I think we need to understand. I don't think we have enough understanding. And unfortunately, people who understand, at least to some level, they're not willing to share the data. So we actually really want to create or experimental methodologies that can provide us data. So we need methods for vulnerability modeling and discovery. And this should really be based on real device data, which could guide models later on. We also need to do better architecting. So co-architecting of system and memory is important, I think. So solutions that are partitioned between memory controller and memory are going to be important, in my opinion. And we need to do better design and test. Okay, I think we're almost done. That's why we've been doing these experiments. So this was a challenge and opportunity, and I think this is just the tip of the iceberg. So we want to build fundamentally robust, reliable, secure, and safe computing architectures. And I believe we need intelligent controllers to enable this. Okay, as I expected, we didn't get to the next part, but maybe we can get to it later.
Absolutely. So I think that you've raised a number of just amazing and interesting topics, and thanks for the deep dive on one of the really important topics. So with that, please, a round of applause for the presentation. Thanks, Onur. So we're close to the end of the hour, but we'd love to get any additional questions. Let's start with any locally, and then if people can just use chat online to post questions. Let me just run around with the microphone. So.
So just like the RowHammer and its equivalent row, the other one, are there any similar known vulnerabilities that exploit hardware at a physics level? Are there any vulnerabilities which are as dangerous as this one, but are already known? Like you explained extensively about one. Are there more than that?
Okay, I mean, that's a... If you're talking about like bit flips like this, I don't know of any vulnerabilities. I mean, if you look at, for example, SSDs that I kind of brushed over here, there are a lot of robustness issues over here, but you have an intelligent controller sitting next to the SSD fixing a lot of those issues. As far as I know, there is no other very well-known vulnerability. People publish some vulnerabilities, like using the voltage scaling errors, but they're very hard to, let's say, induce in real systems today. I don't have an equivalent to RowHammer or RowPress today, as far as I know. But hopefully we'll have more so that we can understand.
One online question,
yes.
Is SRAM vulnerable to these sorts of attacks?
That's an excellent question. I mean, people have clearly demonstrated read disturbance, write disturbance issues in SRAM, especially when it scales to very small node sizes and also low voltages. I think people have also tried to do this on real systems. But I think one of the issues with SRAM is it's relatively easy to solve the problem. Right? You can have large amounts of ECC on processor caches, and that's why I believe people don't see a lot of scaling issues like this in SRAM today that are exploitable.
And there are also active circuit elements which can make the design more robust.
Yes, exactly.
Okay. And another online question was, which of the other memory technologies, which do you think are either most promising to be less vulnerable to these issues, or is it too early to know?
I believe it's too early to know, but I don't have, let's say, a positive outlook. I think there are a lot of interesting technologies. This is only a small subset, right?
Yes.
People are working on other technologies also. I think in the end, as you reduce the size of the cells and the circuit elements, you're going to run into these robustness issues.
Yes.
And in the end, you'll need to protect them.
Yes.
I believe the solutions can actually be somewhat similar at the higher level, right? If you can have an intelligent controller that could actually understand the device level technology and fix some of those issues.
Yes. Now, this seems like a really fascinating issue because there's obviously physics and all of the technical issues, and the layered architectural approach we have. In a way, this sort of is violating an architectural contract. But also it's compounded by the industry IP and issues around companies not wanting to be sort of open about the issues. And so that's obviously made it much more challenging to really address it too. So a fascinating combination of issues. Time for maybe one last question locally. Great.
So if we're not willing to give up security for performance, how many % will we lose with current techniques?
Oh, okay. That's an excellent question. I think I will refer you to some of these papers that we have coming up. So it depends. Again, it depends on the threshold, RowHammer threshold. If your RowHammer threshold is low, existing techniques can incur existing solutions, state-of-the-art solutions, which we didn't talk about, the academic solutions. Usually these academic solutions actually have some counters, not per row counters, but some counters like using hashing, using Bloom filters, etc. And they try to refresh or throttle accesses. Unfortunately, as the RowHammer threshold goes to, let's say, 100, they still induce performance overhead like 10% on the average case. But there may be some applications that access memory a lot, and they could lead to performance overheads of 30%, 40%, 50%.
Great.
So it really depends on the use case. So that's why I don't want to give a single number. It also depends on the application.
Awesome. So thanks for a really great talk. There are a number of really excellent YouTube videos, but as you should know, all of these presentations and videos do get posted on the SystemX website under the E310 seminar page, usually within a day or two. And every one of these slides has a link to a paper. And so if you want to learn more, I recommend just looking at the presentation and clicking on the links to see some of the underlying detailed research. So thanks again for a great presentation. Thank you very much.
Thank you very much. Thanks for the questions.